I want to spend the rest of the time going over a few examples and talking through a couple of things here. And we might end a little bit sooner, but we'll see. So I want to highlight one paper written by this guy, Roland Winston, who's considered the father of the field of non-imaging optics. Essentially, the idea here was to demonstrate irradiance on Earth that exceeds that on the sun's surface, which sounds pretty crazy, right? So, so how does that work? And this was a paper in 1989, published in Nature. So let's take a quick read through the couple of things that I highlighted. So the flux at the surface of the sun, which we have seen before, is approximately 6.3 kilowatt per centimeter squared. Okay, so that's what's coming off right at the surface of the sun. And it falls off with distance, right, as a inverse squared, as we know. And it falls off to something like 137 milliwatts per centimeter squared above the Earth's atmosphere. And once it passes through the atmosphere, as we know, it goes to something like 80 to 100 milliwatts per centimeter squared. So again, we went from kilowatts to milliwatts. That's a 10 to the 6 here, 10 to the -3. That's a reduction of 10 to the 9. So that's an incredible change in magnitude, just to keep in mind, because the sun is so far away. Obviously, it's a good thing because otherwise we won't survive. So in principle, the second law of thermodynamics permits an optical device to concentrate the sunlight to obtain temperatures at the Earth's surface close to the sun's surface temperature. Now, and we can enhance the temperature by using a refractive index of material that's higher than 1, as I showed you just recently. However, of course, in a practical sense, this falls short because all optical systems are not 100% efficient. There are some losses involved there. So now, non-imaging light gathering devices can improve on the imaging designs. That was the purpose of this paper, by a factor of 4 or more, and approach the thermodynamic limit. And they essentially used a non-imaging design, which we'll see shortly, to concentrate terrestrial sunlight by a factor of 56,000. So that's a pretty incredible concentration factor, producing an irradiance that could exceed that of the solar surface. So that's the remarkable thing here. This opens up, of course, new applications of making use of solar energy. And it certainly has, and it's one of the key units used in concentrated solar power, in very high efficiency concentrated solar power. For instance, things we are thinking about for the moon, permanent base on the moon, and Mars missions and so on. Now, how does it work? There are 3 steps to think about. First of all, here we have the sun. Of course, this is not drawn to scale, as you can imagine. First step, the sunlight bounces off the 40 centimeter mirror. So there's a big mirror here, 40 centimeter diameter, silvered mirror. And it's a focusing mirror, so it's concave, so it focuses, as you learned in your lecture, and it inputs to this surface here, which is a silver conical non-imaging optic, and it's like a CPC. And that CPC, which is shown as a silver cone, squeezes the light from 1 centimeter, that's its input aperture, to 1 millimeter. So here we went from 40 centimeters to 1 centimeter to 1 millimeter. So that's a 40x concentration here by the mirror, and 10x concentration by the silver. So that's a 400x. In terms of the actual Tendu is 60,000 times brighter than normal sunlight, because you square this basically. Oops. So approximately. So there's of course some losses there, so it's not exactly the same. On the right-hand side, you see just a detail of the CPC-like device. It's not exactly a CPC because it's 3 dimensions, so they optimized it using some computer software. So here is just showing an edge wavefront coming in and getting focused to one edge, just like the edge ray principle as we showed before. Now, it's also illustrative to kind of take a look at how this experiment was done. So again, the same as before, you have the primary mirror shown here, collection angle here, and it's going to this non-imaging secondary concentrator, going to a calorimeter, which measures the temperature. And the details I won't go into, but you can see here, they use a oil-filled silver vessel. So that's where the N is greater than 1, because the refractive index of the oil is greater than 1. So that is how it, actually, no, that's actually not true. That was my mistake, sorry. This oil is just to cool the silver. So the silver device is shown here. An image of the sun is formed as an input, but because the mirror is an imaging element, so it forms an image of the sun, but the concentrator does not form an image. It simply takes all the energy in that image and funnels it into a very, very small region here, which is then collected as heat in this very tightly calibrated calorimeter that you can see. And if you're interested, take a look at the paper. It's actually quite good, quite useful. Now, I'll come back to that later. Now, I want to spend a little bit of time thinking about some practice problems, and let's spend a little bit of time here on this. So first, I want to show a very simple demonstration of a tracker that attempts to use solar energy. And I want you to pay attention to this very simple idea, and then think about how you might improve on this. And I'm going to ask you to brainstorm for about a minute or so thinking about this. And again, at that time, you can talk with your neighbors or chat on if you're online. So let's take a quick look, and I'm probably going to speed through this a little bit. Okay. Let me show the final. Yeah, so it's a turntable driven by a motor. It's a nice project from a middle, I think a middle school, and you have solar cells, and okay, I'm gonna fast forward to the final demonstration, which is more interesting. Out here. So okay, so there's a solar panel, there's a motor, and you have the idea is to move this so we want the turntable to track it such that as the sun moves, you want it to move towards the sun, right? So it's a solar tracker that utilizes solar energy. So that's pretty cool. And they also do the experiment outside, which is more interesting. I mean, it works okay, but that's the idea. So I'm gonna, oops, sorry. I'm gonna pause here and now give you a second to think about, discuss this. Oops. I guess I need to play. So feel free to discuss. I mean, my question for you is how would you improve this kind of a design? I need to figure out how to get out of this. Sorry. Yeah, let's take a 30 seconds or so. Oh, I can get out here. There we go. Sorry for that. Okay, so I want you to think about, okay, some ideas on improving this. Let's take a 30-second break and think about this, and maybe some of you might have some ideas that you can share.
Have some idea, you can like speak up. I guess a professor can hear you, right?
Yeah, I can hear you, or just put it on chat, or yeah, Ikata, you can relay it. Yeah. So again, let me. I guess I didn't formulate the problem properly. Let me rephrase this, I guess. So the idea is solar panels need to track the sun in order to get the best performance, because we know that when sunlight comes in at an angle, the collection of light is reduced. And we'll talk more about it later in the class. So generally, we have to track the sun. And this is particularly true for concentrators, because concentrators have a fixed acceptance angle. So actually, I should probably draw this. So if the sun is here, and I have the CPC collecting, when I draw the sun here, the CPC here. Okay. And I'm going to get straight lines because the sun's far away. Now, and everything is good. I can collect it onto the solar cell. But if the sun is over here, I'm going to get rays that are outside the acceptance angle. And my acceptance, of course, if this angle theta is greater than theta input is greater than the acceptance angle theta, then I will not collect anything, right? And the only way to solve that problem is to track the sun by moving the CPC like that, right? I have to tilt the CPC. And that's kind of what this project was all about, was to tilt. In that case, there wasn't a CPC, it was a solar cell, by using another solar panel to drive a motor and adjusting the polarity of the motor in order to follow the sun. So I want you to think about some ideas on how this could be improved. Of course, yeah, I'll show you another example shortly, but let me see if there are any ideas. And this is clearly a problem, right? As you can imagine, because to track something heavy requires energy, and you don't want to spend more energy than what you're creating. Any ideas?
Solar panel pitch, so it's not only facing the sun, but it's at the opposite angle to receive rays.
If you are facing an angle, then there is some shadow of that CPC again.
Yes.
So you have to consider that one too. So if you are
that is
moving
correct.
in a specific angle, it should not be that correct. So you have to think like that. Did you hear about it's about the discussion? Did you hear about the line tracker of a robot or something? It's a path tracker. So it's like the same thing. Like if you're going to track something, you need to put some sensor like around that. So you can think like that way. Like if the rays are coming to this, okay, 50% are covered or not. You can if you can measure that one, we have to move it in that way. If this portion is getting some sensor of the light or something electric, so you have to move it under. So if like this is the thing, 4 tracker is there. If you think like 4 sensors are there, if these 2 are getting reflected by some of that, you have to move it in this direction. Like the whole total thing have to move in this direction. So that's the thing, you can cover the whole area, but you have to think again on the tilted version too. So yeah, you can like, it's a motivation, like you can motivate your thinking like this way. So feel free to discuss.
Yeah, that's a great, it's a good point, Kata. Yeah, Nathan in the chat has a very important point. So this is a really good way to. So we can think. So I want to just draw the solar. So far we've been thinking about. This is the solar panel. We were thinking about just tilting the solar panel, right, to track the sun as the sun moves. But you could also think about using mirrors to ensure that the angle is the same as the sun moves. And this is what Nathan's saying. So we can keep the solar panel the same, but use, let's say, a mirror. I'm going to just draw this roughly for now. As the light comes in, I'm going to have it perfect like this. But if I have a different situation and the light's coming at a different angle like that, let's see, can I do it? I can tilt the mirror such that I can maintain this angle. You see? So, and that's another solution. And sometimes this might be better because the mirrors might be easier to move than the solar panel. That may be excuse me, thinner or lighter. And this solution is also called a heliostat, and we will see this many times when we talk about again, I won't say many times, but we'll see it again when we talk about solar thermal systems. In fact, my next example is related to that. So this is a good segue to go to that. So this is an example from a few years ago from an ARPA-E Innovation Summit. So let me just play that from a startup company called Other Lab. So I'll let it play for a second.
Sorry. Okay. No, I guess. So the sound is not here. The video.
Oh. Okay, hold on.
Yeah.
Yeah, so you can't hear the sound?
Uh-huh.
Is that what you said?
Yeah, we can't hear.
Okay, let me see where that is. I can, if you can't hear it, that's fine. I can. You still can't hear it? Maybe turn up your volume.
Like your voice is okay.
Okay, that's fine. I can narrate it. So, I mean, basically, she's talking about the fact that you have to expend a lot of energy in order to track the sun. So they're developing a new type of solar panel which uses hydraulics. So it uses these tubes that are shown here, and they inject water into each of these tubes, and they control how it bends, and that creates an actuation mechanism. So I'll show you an example. So there you see the mirrors. So these are the heliostats that I was talking about. It will reflect the sunlight, but of course we need to point these mirrors in two axes, right, in order to track the sun in two axes. So, and this is only a portion of the sun, and then you have another one next to it, and so on and so forth. And these are usually deployed in very massive fields, like over thousands, hundreds of thousands of them, over kilometers potentially, to collect huge amounts of sunlight. And they are designed a very small prototype as a proof of principle. Now, the wind loading is an issue, because you could imagine if you put this in the desert where you really want this, when you have a lot of sunlight, the wind can can pick it up and cause damage and things like that. So they're going to show some tracking by they're essentially distributing water into each of those tubes to control how it moves. And this is, of course, in a way inspired by what happens in nature with flowers and things like that, right? Flowers essentially follow the so they have a central control system which allows them to essentially route the water, in this case, to different portions of the different parts of the tracker. And I'm gonna pause that and go back. Oops. can this cause some problems? So let's see. Okay, that's good. So yeah, so I would say that's another example of a excuse me, a robotic tracker, but the tracking happens with hydraulics as opposed to electrical motors, as you saw before. And it's a different sort of innovation because they're trying to essentially centralize and use control software to optimize how the tracking actually happens, how to allocate the hydraulic pressure on the different mirrors and so on. Turns out to be a controls problem. So I want to give one more practice example now. I want you to, so now we've talked in 2 lectures about non-imaging optics. I want you to, and you know, another 2 lectures on imaging optics. I want you to think about this particular problem as a practice. Design a concentrator that concentrates sunlight into a ring, not a spot. So far we've thought about a spot, but how do you concentrate it into a ring? Now there might be some situations you want to do this. For instance, in the example in the paper I showed you, there was a concentrator that might shadow the sun because it's in the same path as the big mirror. So if you could have concentrated into a ring, you could avoid that shadowing effect. And there are other examples of this. So let's take about a minute or so and think about, maybe more than a minute, but think about this problem and see if you guys can come up with a solution. So again, the idea is that I have light coming in. Oops, I have light coming in. I want to design a system such that I want to concentrate and create a donut shaped, I'm drawing a cross section, spot. Okay. All right, let's think about this. And feel free to discuss among your neighbors or chat online. And there might be reasons why you might do it. For instance, in the case of, we'll actually see an example shortly, but in the case of solar refrigeration, a very old idea is to create a pot in a pot, something called a Zier pot. We'll talk briefly about it later, where you want to ensure that the sunlight does not directly reach this central portion here, because that's where you want to keep the food or milk or whatever that you want to keep cool. But you want the sunlight to go outside such that then it can be used to run a heat engine, for instance, as a hot part of a heat engine. But anyway, that's just another example. Okay, actually, maybe I'm going to leave this as a, unless, okay, let's see. Are there any interesting solutions or ideas? Okay, let's see some character. If you put a lens above the surface, so the surface is past the focal point. That's a good comment. What he's saying is that I have a lens and I focus and the light diverges. So that's of course the focal point. What if I put the object down here or here? Now that depends on the design of the lens, but generally speaking, this will just be a defocus spot that may not form a ring. So that may not solve it. But if you design the lens in a very specific way, that can actually be done, but that we haven't learned that yet. That's a good suggestion. I mean, a very simple thing you can do is do what Jared just suggested, but simply put a shadow and block it off, right? That's kind of a trivial solution. So I can put like a shadow on top here and simply block off, and then I have a region that's very bright outside. So that's kind of it. How do I say it? A more brute force kind of solution. But I think in the interest, I want to talk about one more topic. So in the interest of time, we're going to move on, but I'll leave this as like something that you can think about at home. And if you have some ideas, of course, you can message me. I'm curious to hear your options, and some of you might find this useful in your projects. Okay, before I go on to the next topic, I also want to just highlight a very interesting TED Talk by Bill Gross. He's an inventor and entrepreneur and so on. The talk is a little bit old, but it talks about solar thermal energy and how it can have a pretty big impact on the renewable energy field. Now, I want to show this video, and hopefully I'd like the sound to play. So let me see if I can, maybe if I move my headset. And I want to play this video, and I want to talk a little bit about this paper. So let me first play it.
We're living on a warming planet.
First of all, Ekata, can you hear that?
Yes.
All right, so I'm going to play. It's only 2 minutes. So I'm going to just play it through, and then we will look at the technology in a little more detail. And that's the last topic I want to talk about.
Species, including our own, forced to adapt or eventually die under the assault of excessive heat. We've seen that an increase in certain gases in the air has the effect of turning this planet's atmosphere into an ever more efficient greenhouse. Heat energy arrives from the sun, but can't radiate away. But even without the addition of these greenhouse gases, the fact is huge portions of the Earth's surface are simply too hot and humid to allow people to live and work in reasonable comfort, causing some regions of the world to lag behind in progress, prosperity, and public health simply because of excessive heat. Now, since the 20th century, our answer has been to turn on the air conditioner, and this has worked, liberating tropical regions of the planet, beginning with America's own South, from the oppression of their own climate. The trouble, of course, is the more you improve people's lives this way, the more people will want their lives improved too. The demand for temperature control is growing, not just to cool homes and offices, but to refrigerate food, medicines, the basic necessities of life. More air conditioning means more energy production, which introduces more greenhouse gases, warming the planet further in a vicious cycle with no good end in sight. Which makes it all the more intriguing that less than 70 miles away from all these problems, you find one of the coldest places you could imagine, outer space.
You can say it's the sky, but what really matters is what's on the other side of the sky is very cold. Conventionally, if you think about how cooling happens, you need to have, the heat needs to go somewhere colder. Right, that's how cooling happens. So the heat always flows from hot to cold. If you just have air around you at the same temperature as you, there's no reason you should expect it to go colder.
The good news is that barrier is not impenetrable. Heat absorbed into the air, the ground, your house, radiates away again in the form of infrared light. And some of that light, within a certain small range of wavelengths, manages to radiate straight through our atmosphere and into the cold of space. This takes place naturally, and people have known about it for centuries. Ancient Middle Eastern cultures, for example, used this phenomenon known as radiative cooling to create ice for their own use, even in regions where the ambient temperature never goes below freezing. Now, researchers have found a way to manufacture special materials that will radiate the sun's heating energy back out at the precise wavelengths of infrared light that allow that heat to radiate through the wavelength window and vent directly into space, even in broad daylight with the sun beating down. It's an entirely passive process requiring no energy input to work. Once installed, these materials produce temperatures cooler than the ambient temperature around them, reducing the workload of a standard air conditioner by as much as 10 or 20%. With electricity demand expected to rise dramatically in the coming years, and much of that coming from increased air conditioner demand, a passive cooling system like this requiring no energy to operate beyond the dynamics of the planet itself might just allow us to address the needs of a warming planet without making those conditions worse.
Okay, great. So that's a really interesting idea, and it's relevant to what we talked about so far, because again, we're treating these as black bodies, right? So in this example, the black body of outer space, the outer space itself is considered a black body, and that's the cold end of this heat engine. And the hot part is, of course, the surface of the Earth, which is hot because it has received the energy from the sun. Now, what is happening is that because of the greenhouse effect, we have a shift in the equilibrium. In other words, the gases in our atmosphere prevent some of the radiation. So of course, the Earth is a black body. It's going to emit at the same wavelengths that it absorbs. But the problem is that not all those wavelengths escape the atmosphere. And it's a good thing, because otherwise it'll be very cold, right? We won't be able to live here. But we want some of it to escape, but we have just made the problem worse by changing the atmosphere. So it has increased the amount of energy that's trapped by the atmosphere. Now, what this technology is talking about is trying to shift those wavelengths of light that are emitted by these special panels on Earth, such that they escape the atmosphere into space. Now, if you can do that efficiently, then you can try to cool down the ambient temperature. And that was what was reported in this paper that I want to kind of highlight briefly. It was again a paper in Nature not too long ago from Shenhui Fan's group, and Ashwath Raman, who was on the interview, was the graduate student who worked on this at that time. The title of the paper is interesting. It's a passive radiative cooling below ambient air temperature under direct sunlight. What does that mean? That means that they designed and built a device that allows radiative cooling such that the region is near the device is cooled to a temperature several degrees below that of ambient temperature under direct sunlight. That had not been done before. So I'll just highlight a few things here. First of all, this is the main point. When exposed to direct sunlight exceeding 850 watts per square meter on a rooftop, the photonic radiative cooler cools to almost 5 degrees below ambient air temperature and has a cooling power of 40 watts per square meter at ambient air temperature. Okay. The idea, again, is kind of cool, because here the idea is to utilize the cold darkness of the universe as a renewable thermodynamic resource. So that's a cold part of this heat engine, even during the hottest parts of the day. So that was the cool idea. Of course, it's not a new idea, as pointed out in the paper, but they developed this new device that could be done, that could be manufactured relatively inexpensively. Now, I'll highlight a few things about the math which are relevant, because it's very similar to what we talked about. But let me actually show the picture first. Oops. Oh, the picture. So the picture is kind of missing, but so this equation is something should be familiar to you. So here they're talking about cooling power, which is equivalent to the radiative flux that we talked about, the phi. So that's a function temperature. So this is how much radiative power is coming into the system. This is how much radiative power is escaping into the atmosphere. This is the radiative power escaping the system. So that's why it's positive. This is the radiative power coming into the system from the atmosphere. This is coming from the sun, the atmosphere, because the ambient temperature is also hot, right? It has some temperature. And this is the heat lost by conduction and convection. So, or heat gained in this particular example, because it's a negative sign. And all of these can be expressed in terms of what we are familiar with, which is basically the second equation talks about integrating over the solid angle here, which we haven't talked about. But this integral we have talked about, which is integrating over the spectrum, d lambda. Now here there's a black body spectrum, which we talked about, but there's something here that's new. It's called the emissivity, epsilon. It just means how efficiently does this material emit light at that rate. Okay. So I think some of these are familiar. I won't go into all the details. This is the spectrum of the black body, which we saw before. It's exactly the same. And the integrals can be worked out, but there's a very interesting conclusion here I want to kind of point out too. The energy from the sun is shown here, which again is relatively familiar to us. It's the intensity, the spectral irradiance from the sun, M1.5 at the bottom on the Earth's surface. The emissivity of the sun, which we assumed was 1 in this example there. They're going to assume 1. I'm just putting it there for completeness. And then the area of the sun. It is the absorption. So it's the area of the device that's used to absorb it. And then they use something called the Krykov's radiation law, which is basically conservation of energy, which is this expression here. And then they plug in some other numbers on convection, and they have some equivalent models for conduction and convection. It's not terribly important here for now, for purposes of discussion. And the idea is that if they can increase this term, this first term, more than these other terms, then you can make this P cooling positive, which means that now you can cool down this object. That's the idea. So you want to make this temperature T to be less than the ambient temperature Tm. And that's exactly what they did. They designed a device such that this is higher than all these terms. And I won't go into the details of how it works, but you can see a picture of the device here. And they also made another interesting innovation, which was to design this to be quite separated from its environment. So let's think about this for a second. First of all, there's this wood frame here, which is a good insulator, so which you can see here. Then they have this clear acrylic suspension, and it seals this region here. This region is completely sealed, forming an air pocket. So that is a really nice, because it allows you to create a closed system. And the rest of it's relatively simple. They have a polystyrene backing here, which is an insulator shown here. They have an aluminized mylar at the bottom. They have also on the top, just to reflect the light. You also want to reflect as much light as possible. And the yellow stuff is this photonic radiative cooler. They have a low density polyethylene plate at the top to prevent wind damage and things like that. But it is very transparent to all the wavelengths coming in and out. So that is just for protection. And as you can see in the picture here, it shows exactly what happens. They tilted it to face the sun. In this case, this was done in the winter, so it's tilted 30 degrees, and that just reflects the Bay Area latitude. And so the light coming in, some of it's reflected off, and then there's these red arrows show the radiative cooling that's happening. Now the details, if you're interested, of the actual photonic radiative cooler is shown here. It's a multi-level structure with different materials, and it is designed using computational techniques in order to emit at those wavelengths that are transparent relative to the atmosphere. Now, I won't go into the details, but they're very precisely defined. But the nice thing is that these can be deposited over large areas, potentially at low cost. Not quite low cost yet. They're trying to do this through a startup company, but it's not quite there yet. So the spectrum is important. So that I told you before, the reason this works is because of the spectrum. So they say M1.5 spectrum. This is the emissivity of the photonic device. You can see it emits. It's the same absorptivity. It's very low absorption, where the M1.5 is peaked. Its absorption is high at very low wavelengths. Also, you can see this is nice. And if you also look at the emissivity of the cooler, that you can see it coincides with the atmospheric transmittance. So you can allow the light between 8 to 13 microns is emitted in that wavelength range, which is with the atmosphere transparent to, so it will go out into space. So this is the measured emittivity of the cooler at 5 degrees incident over mid-infrared wavelengths using a polarized light source. Okay, so it achieves this strong selective emission within the atmospheric window. Now, of course, this is the most important experiment, but that they did here. The horizontal axis is the time of the day they set it up, and then they start measuring it starting around a little before 10 a.m. and they measured the temperature. So this is what happens very quickly because of radiative cooling. The temperature drops below this is the ambient temperature shown in black. The photonic device goes below the ambient temperature very quickly and maintains that over the course of the day, several degrees below, as you can see. This green plot is just the solar radiation. just to show. Of course, it increases over the time and decreases in the evening. They tried a lot of different materials just to show, okay, if you use simple aluminum to reflect the light off, it actually does gain heat temperature. So the aluminum is not good enough. Black paint, of course, is a black body. It'll absorb all the light, so it actually gains the most temperature. So that's just to show calibrated measurements. And they have some other nice experiments that were done during the day as well. So this just shows the radiative cooler. As soon as you turn on the radiative cooler, it actually starts dropping the temperature. Okay, so this is a really, really interesting example of a completely passive cooling, right? That it takes no energy at all. So that's something for some of you to consider, for those of you working in the field of passive radiative cooling. With that, I think we will stop today. So let me see if there are any questions. So we're going to end a little bit sooner. Early, and just to remind ourselves, make sure that you submit your assignment on Tuesday. Let me know if there are any questions. Try to get the Light Tools or Code 5 software to work before Tuesday. If you cannot, it's okay. There are other options, as I mentioned at the beginning. Again, let me know if you have any trouble getting these things. Any questions before we end? Katha, I can't. Sorry.
Yes, no question. Yeah.
Okay, great. So we'll end a little bit earlier today, and if you have time, make sure you connect with your teammates about your presentations. I mean, the next assignment and the presentation, they're both team-based presentations. Only one of you have to submit, of course, just like before. Okay, great. Thank you all. See you next week.